So, we're in Chapter 3, Section 3. We are looking at applications of the derivative, and we're focusing on ways we can use the first derivative, or use derivatives, period, to look at curves, look at functions, look at what's happening, get an idea of what the graph should look like. So in this section, Section 3, we're going to focus on increasing and decreasing functions and the first derivative test. So of course, we're going to determine intervals on which the function is increasing, our intervals it's decreasing, and learn about the first derivative test. So just so that we have a definition, we're both all on the same spot. We have defining an increasing function on an interval means that any place in that interval, any two numbers that are on the interval, if x1 is smaller than x sub 2, then f of x sub 1 is smaller than f of x sub 2. So as x gets bigger on that interval, the value of the function is getting bigger. And decreasing, as x is getting bigger on that interval, the function value is getting smaller. So it's pretty much duh, but again, we want a formal definition so we can work with this. Our test, now when we talk about if a function is increasing, that means going back, thinking an idea as well, when it's increasing, it's kind of going upwards. It has a positive slope. If it's decreasing, it's going to have a negative slope. We can find the slope by looking at the first derivative. So this test basically says if the first derivative is positive for all values of x on an interval, then f is increasing on the entire interval. And if the derivative is negative for all values of x in the interval, then f is decreasing on that interval. If there's some positive, some negative, then you have the wrong interval because it's not doing the same thing. So that's the big trick on here. If the derivative is 0, then it's constant. So let's see what this means. Let's work with this function right here. Oh, okay. So f of x is x to the third minus 3 halves x squared. We want to use the open intervals on which it's increasing or decreasing. So we will start off, we're testing it with the first derivative, so we'll find the first derivative. 3x squared minus 3 halves times 2x. And my 2's cancel, so this is going to be 3x squared minus 3x. Or, since I have a common factor, let's take it out. 3x times x minus 1. The reason I do this is we want intervals on which the first derivative is always the same value. If we are looking at a function that is continuous and differentiable, the first derivative is also nice and continuous. The only place it can switch from being negative to positive or positive to negative is if it goes through 0. So we're going to look and see where does the first derivative equal 0. And that's going to give me x equals 0 or x equals 1. So I can break this function into 3 intervals. We can go negative infinity to 0, 0 to 1, and 1 to positive infinity. Because nowhere in this does the derivative hit 0, so nowhere can it switch from positive to negative or back or forth. So we say, what's going on here? If I am less than 0, is what this is saying, then 3x is going to be negative, and x minus 1, negative number minus 1 is going to be negative. So I have a negative times a negative gives me a negative number. So this is going to be decreasing. If x is between 0 and 1, well, x is positive, so 3 times a positive number is positive. A number less than 1 minus 1 is going to be negative, so we have a positive times a negative. That equals a negative. I messed up over here, sorry. Negative times a negative is positive. Sheesh. Let's fix this up. I know you were yelling at me while I was going through here. This one, though, is definitely negative, so this is going to go down. If x is bigger than 1, again, 3 times x is going to be positive. Number bigger than 1, take away 1 is still going to be positive, so we get positive times positive is positive, so this is going up. So my open intervals, we're going to be increasing on the intervals negative infinity to 0 and 1 to infinity. And we're going to decrease on the intervals from 0 to 1. So that's kind of using the derivative to help us see what's going on. Our big key here is where the derivative is going to change sign from positive to negative or negative to positive is going to be where it crosses 0. So here's that function we just did, x cubed minus 3 halves x squared. And you notice when we're less than, whoops, let's go back. When we're less than 0, it's increasing. Get to 0, it starts decreasing until we get to 1. It starts increasing again. Now here's one. It's increasing until it gets to 0, and then it starts increasing again. This is what we call strictly monotonic. Monotonic means it's only one direction. Now this one, it looks like it might be strictly monotonic, but it's not, because right here it's not increasing. Here it's constant. Between 0 and negative 1, we're at 0. We're at a constant value. So this is what we're talking. Is it getting bigger? Is it getting smaller? First thing we can use derivatives to help us with. So here's kind of a guideline. How do we do this? Step by step. So we need to be continuous on the interval. It needs on this open interval. So the first thing we're going to do is look for the critical numbers in that interval. We're going to use those to find our test intervals. Again, the critical numbers are either where the derivative is 0 or where the derivative does not exist. We're then going to look at each of those intervals and find the first derivative. Well, we're going to find the first derivative and test. And we just have to test one value. And it doesn't matter. Just test one value in each interval and see is it positive or negative. Because it's going to be the same for the whole interval if I found my critical numbers right. And then I look at my theorem to say, am I increasing or decreasing? So we use this to get to the first derivative test. Ooh, this sounds important. First derivative test is basically looking for extrema, relative extrema. It says if it's continued, the function is continuous on an open interval and is differentiable on that interval except possibly at c, then if the derivative changes from negative to positive, it's a relative minimum. If it changes from positive to negative, it's a relative maximum. And if it doesn't change, then it is neither a relative minimum or a relative maximum. Makes it a little bit more sense maybe if we look at it with pictures. So on here, it's negative and it switches to positive. And this point where it switches from negative to positive is my relative minimum. this point where it switches from positive to negative, that's going to be my relative maximum. Remember from the song I Will Derive, to find where it's at a maximum, we look for where the derivative is 0, because that's where it's going to be. It can be a relative extrema. If it's going up, then it's going up. Going down, it's neither. It's not a relative extrema. So that's that first derivative test. Hardest thing about the first derivative test usually is finding the first derivative. That's going back to some of the stuff we did in chapter 2. So let's work some examples. Oh, we're jumping ahead. So let's just do, if you think you can want to try this on your own, pause the video. I'm going to go through and work one of these just to kind of show you what we're doing. Again, here we're looking on an interval 0 to 2 pi. So I'm going to start off by finding my first derivative. Because I need to set up those intervals. I need to find where those critical points are. I'm going to do that with the first derivative. Derivative of 1/2 x is just 1/2. Derivative of sine x is cosine x. I look and see where are my critical values. I'm going to set my derivative equal to 0. So 1/2 equals the cosine of x. So the cosine of x equals pi over 3 or 5 pi over 3. So I can set up my intervals. Now here I'm not going to infinity because I'm only looking on the interval 0 to 2 pi. So my first interval is going to be 0 to pi over 3. My second interval is going to be from pi over 3 to 5 pi over 3. And then I'm going to go 5 pi over 3 to 2 pi. So those are the 3 intervals, the 3 places that I want to look at. On each of these intervals, it's either increasing, decreasing, or constant. The only places it can change is at these critical values. So this is my first critical value, pi over 3. This is my second one, 5 pi over 3. These are the places that could be our relative extrema. So we just pick a value between 0 and pi over 3. I'm going to pick pi over 4 because that's the one I know. So I plug this into my first derivative, 1/2 minus the cosine of pi over 4 is 1/2 minus the square root of 2 over 2. And I know the square root of 2 is bigger than 1, so this is going to be negative. I don't even care what that number is. I'm only looking to see positive or negative. So since this is negative, it's going to be going down. I'll look between pi over 3 and 5 pi over 3. I just need to pick a point. If I have an easy one to pick, let's pick it. I like pi over 2. Because 1/2 minus the cosine of pi over 2 is 1/2 minus 0. So that's going to be bigger than 0. So it's going up. 5 pi over 2 to 2 pi. Let's pick 7 pi over 4. Because again, that's one I know. I don't even have to grab my calculator for it. I don't need my calculator. That's so much nicer. So that's, again, 1/2 minus square root of 2 over 2. So that's going to be less than 0. So this is going down. So we look at this. Here we're switching from negative going down to going up. So this is a relative minimum. This one we're switching from up to down. This is a relative max. So the relative extrema, we're going to say we have a relative minimum at x equals pi over 3. And I can plug in and find that point. If I plug in pi over 3 into 1/2 x minus the sine of x, I will get a negative 0.312. My relative max is at x equals 5 pi over 3. So plugging that in, I'm going to get 3.484. So when I'm trying to find the relative extrema are at these 2 points. These are the x values. I plug them into f to find out what those values are. That's the idea. Just going to practice a couple more of these. So let's clear this one off. And why don't you give this one a try? So pause the video, see what you can do with this one. Watch out for the chain rule right here. Let's give this a try. The first derivative is going to be, well, I'm going to use the general power rule. So I'll go 2/3 times x squared minus 4 to the negative 1/3 power times the derivative of x squared minus 2, which is 2x, using the chain rule. So we'll work this together. That gives me 4x over 3 x squared minus 4 to the 1/3 power. Now when I look for critical values, the first things I'm going to look for is, notice here, I got x in the denominator, so x equals 2 or negative 2. The first derivative does not exist. So that means those are critical values. Critical values are where the derivative is 0 or where the derivative doesn't exist. Where I want the derivative to equal 0, I don't worry about the denominator. So as long as the denominator is not 0, the only thing that's going to make it 0 is the numerator. So I'm just saying 4x equals 0, so x equals 0. So those are my critical points. That gives me my intervals. Now this is just saying on the whole function, so I'm going to go from negative infinity to infinity. So we got negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. And again, I need to just test a point. I don't care what point, as long as it's on that interval. If it's one that I can, makes it easier for me to calculate, I do that. Otherwise, I just plug a number in, use my calculator. So I just went ahead and said, oh, between negative infinity and negative 2, I said, oh, let's try negative 5. Plug that in. If you plug in f, the first derivative at negative 5, I plug it into here. It's a negative number. That's all I care about. I don't care what the derivative is. I just care positive or negative. For here I tried negative 1. And the first derivative at negative 1 is going to be positive. X equals a negative 1. X equals a positive 1. When I did the first derivative evaluate the first derivative again, at 1, this is going to be negative. And then I checked 5. F prime of 5 is going to be greater than 0. Again, I'm just plugging these numbers into my first derivative. And I just do it with a calculator. You can do that yourself. So here we're less than 0. We're going down. Here we're going up. Here we're going down. Here we're going up. So here we change from negative to positive. This is a relative min. Here, this is a relative min. This one is going to be a relative max because it's changing from positive to negative. So when I find my relative extrema, my relative mins are going to be at negative 2. Gives me the point negative 2, 0. And at x equals positive 2, which is the point 2, 0. And we're going to have a relative max at the point x equals 0, which is going to give me the point, come on, 0, 3 point, oops, wrong one, 2.52. So again, we find the first derivative, find the critical values, which again, where it can the first derivative equals 0, or the first derivative does not exist. We set up our intervals based on the critical values and pick a point in each interval to find out positive or negative. We're plugging it into the first derivative, and all we care about is positive or negative. Is it decreasing? Is it increasing? Got one more for you to try. So give this a try, pause the video, see if you can get a good answer for here, and then bring the video back up and see if you agree with what I got. Now, when I looked at that, I said I could use the quotient rule. I'd rather not. But since I have a monomial denominator, I can rewrite it like this. So that's just going to be x squared plus x to the negative 2. The other thing, I jump right into the first derivative, but it's also worth looking at this. X cannot equal 0. This is not going to be a removable discontinuity. This is going to be an asymptote here. So I know automatically when I'm setting up and looking at my intervals, I need continuous on an open interval, so I can't look at the whole thing at once. I'm going to have to break this up into 2 subintervals right at the bat, because right here it's funky. It's an asymptote. So kind of keep that in mind when we're working through this. When you were looking at critical values, again, x cannot be 0. So f prime of x does not exist at x equals 0. But we already know that's a break in our interval, so we're good with that. So then we look at where does x squared... Oh, sorry, I'm getting ahead of myself. I haven't found the first derivative yet. So let's move this down for a little bit. Come on, I need to go, tools here. Okay, cancel. I got to do this right. Sorry about this. Easier just to, we'll move it down here for it right now. Should have just erased it, I know, and redone it. Let's find the first derivative. Much easier to do this one than to have done this one. So first derivative is just going to be 2x minus 2x to the negative third. So again, yeah, we can still say this. The first derivative does not exist at x equals 0. But if I want to find out where does the first derivative equal 0? Let's do a little work on that one. We can move that back up there, yeah. Go back to here. If 0 equals 2x minus 2 over x to the third, I have 2x equals 2 over x to the third. I can cross those out. Multiply by x to the third. I get x to the fourth equals 1. So x equals plus or minus 1. So this first interval, I'm going to break this up into negative infinity to negative 1 and negative 1 to 0. The second interval, I'm going to go from 0 to 1 and from 1 to infinity. But remember, I'm not continuous across here, so I'm not even considering this gap here for a relative extrema. And I know it's an asymptote from what I've done earlier, what we did last chapter, so we know it can't be a relative extrema. So we check our points. And so here I checked x equals a negative 10, and the first derivative at negative 10 is less than 0. So this is going down. Here I checked x equals 1/2, negative 1/2. The first derivative at negative 1/2 is positive. So it's going up. So this is a relative min. When I come over here, I try x equals a positive 1/2. I'm going to get the first derivative is negative again. So here we're going down. And at x equals 10, my first derivative is going to be positive. So we go up. So this is again a relative min. This one does not have a relative max. And that can happen. So my relative extremas, we have relative minimums at negative 1. X equals negative 1, I should say. X equals negative 1. That's actually the point negative 1, 2. And at x equals a positive 1, which is the point 1, 2. Which makes sense. If we look at this, it should be, it has even symmetry, so we should be symmetrical that way. Yeah. First derivative test is based on looking at that increasing and decreasing intervals. So we got to use the first derivative to find these critical values, to break up our interval into intervals where we're constantly increasing or constantly decreasing, and then say where there's a change, that's a relative extrema. So that's kind of what we're doing on here. So here's some more fun for you. Enjoy.